So hello everyone, welcome to all of you, and I'm going to teach you in this tutorial about the energy equation in OpenFOAM. And I'm making this video after a long time, so I'm really sorry for that because I was busy with my academics and PhD. So idea behind this tutorial is that I'm going to explain you that what are the different terms present in the energy equation in OpenFOAM, and also how we can switch between the internal energy equation and the energy equation in the form of the enthalpy. So if you go across the energy equation in OpenFOAM, the equation might be little bit confusing, but after watching this tutorial, I am sure that you have a now better idea that what are the different terms are being present in the energy equation in the OpenFOAM. So in this tutorial I am going to start with the derivation of the energy equation, and after that I am going to show you that how these different terms has been coded in the OpenFOAM, and after that we will also learn how the thermal physical properties is being present in the OpenFOAM. So this is idea behind the complete tutorial series about the energy equations. And I have got also request that the duration of my videos should be little bit smaller. So from now onwards I am trying to create the videos which has the shorter duration. So maybe I will make the videos in the different parts, but I will not keep the longer duration in a single video. So let's start with the energy equations. When we think about energy, so first law that comes to in our mind is the conservation of the energy. So what the law says that the total energy of an isolated system remains the constant over time. Okay, so this principle we need to follow. And secondly, if we think about the energy, so there is a different form of energy. There will be chemical energy, there will be kinetic energy, there will be thermal energy. So there are different form of energy. But when we think about the fluid, so in the fluid mechanics or in the fluid flow, generally there can be two contribution of energy. So if you want to write the total energy associated with the fluid flow, that is can be either the mechanical energy or there will be some thermal energy. Okay, so when we think about the energy associated with the fluid flow, so there can be mechanical energy and some thermal energy. Okay, now these two terms, that is the mechanical energy and thermal energy, can be further expressed into the many different forms. So let's see what can be the different form of the mechanical energy and the thermal energy. So if we talk about the mechanical energy, so there may be some rate of change due to the kinetic energy. Rate of change of kinetic energy. Okay, so this term we can write as a rho dk upon dt. Okay, where k is the specific kinetic energy. I can be written it is a simple form, that is the u square upon 2. Okay, so this is the means the rate of change of kinetic energy, that is the one kind of the mechanical energy. Similarly, if you want to write the another kind of energy, that is the rate of change of stress energy. So this is the rate of change of strain energy, and that we can write as a del dot sigma dot u, where sigma is the mechanical stress tensor. So this is the some tensor quantity. So this quantity you might have heard of in the fluid mechanics, but let me give you some glimpse idea about this stress tensor quantity. So this stress tensor can be further write as a tau minus P into I, where I is the identity tensor and this tau is the viscous stress tensor. Okay, so that is something related to the viscous So this sigma, that is the mechanical stress tensor, can be expressed into the viscous stress tensor and into the pressure and identity matrix. So another form of the mechanical energy could be rate of change of potential energy. Okay, so this could be another form of the energy. Potential energy. Okay, so this term we can write as a rho g dot u. Okay, so these are the different three types of the mechanical energy, that is the rate of change of kinetic energy and rate of change of strain energy, and third one is the rate of change of the potential energy. Okay, these are the major contribution of the mechanical energy into the total energy. Now we can write the different terms of the thermal energy. Okay, so when we think about the thermal energy, so first terms that comes into the mind is the rate of change of internal energy. Okay, so this term we can write is as a rho into dE upon dt. Okay, where E is the specific internal energy. So E is the specific internal energy. Now the second term that is we can write is the rate of heat flux. Okay, so the heat flux can be the another contribution from the thermal side of the energy, resource. So that terms we can write as the minus sigma into del Q. Okay, and so last one we can have a some sink or source. There can be some heat source or heat sink. So that terms we can write as a minus rho into R. Okay, where R is the specific heat source. Okay, so this is the different contribution due to the mechanical energy and the thermal energy. So these are the different terms of the mechanical and these are the different contribution terms of the thermal energy. Okay, so remember that there can be other form of energy sources also, but if we are talking about the heat transfer involving the fluid flow or the fluid mechanics, then majorly this thermal energy contribution and mechanical energy contribution we can think of. Okay, now let's combine all these terms. So this is the total energy equal to the mechanical plus thermal energy, and also we know that the conservation of energy state that the total energy of an isolated system remains constant. Now using the first principle of the conservation law and that mechanical energy and the thermal energy, we can have del dE upon del T, that is the internal energy, del dK upon del T, that is the kinetic energy, where K is the specific kinetic energy, and remember that is the capital K, equal to minus del dot Q, that is the rate of the heat flux, plus rho into R, that is something that is related to the source or sink term, plus del dot sigma U, that is the rate of the change of the strain energy, and plus rho g into U. Okay, so remember that this is something that is the thermal energy, mechanical energy, thermal energy, mechanical energy, and this is again the mechanical energy. Okay, now we can further derive this equation. So these terms, that is the del E upon del T, that is known as the material derivative. Okay, so if you heard of the calculus, this capital D upon capital dt is known as the material derivative. So if we take any phi physical quantity, okay, and if we want to write the material derivative of this phi physical quantity, we can write as a d phi upon capital dt. So this material derivative further can be write in terms of the space and time. Okay, so this we can write as a del phi upon del t, that is the time component, and similarly ux into del phi upon del x plus uy into del phi upon del y plus uz into del phi upon del z. Okay, so if we have 3-dimensional coordinates and if we have time, then this material derivative can be expressed in terms of the space and time. Okay, similarly we can write these two terms similar to this approach. Okay, so we will have rho del E upon del tau. So we can write this rho del E upon del t plus there will be rho u e term. Okay, similarly for the kinetic energy we will have del k upon del t, this is capital K, plus del dot rho u capital K equal to minus del dot q, that is the heat flux. Okay, and this is the heat source or heat sinks. Okay, now this is the del dot sigma dot u plus rho g dot u. Okay, so these are the completely in forms of the local derivative and the temporal derivative. Okay, now these terms, that is the energy due to the strain energy. Okay, remember that I told you that this sigma can be written in terms of the tau minus P into I, where P is the pressure field and I is the identity tensor. Okay, now we can put this term here, so we will have delta dot tau minus P into I into U. Okay, so this we can write as a delta dot tau into U, okay, minus delta dot P into U. Okay, these things we can put here. Okay, this derivation we can put in this equations. So we will have rho del E upon del tau plus delta dot rho u e plus rho del k upon del t plus delta dot rho u capital K, okay, equal to minus del q plus rho r. Okay, now these two terms, okay, this is the two different terms that we are going to put here. Okay, so we can write here plus delta dot tau dot u minus delta dot up or pu, okay, plus rho gu. Okay, so this is the complete equation in terms of the internal energy. Okay, this is equation that you are going to see if you are going to solve for the internal energy. Okay, this is the complete energy equation in terms of the internal energy. Okay, now this again equation can be written into terms of the enthalpy. If you want to write the enthalpy in terms of the internal energy, so we can write is equal to H equal to E plus P upon rho. Now from here we can get E equal to H minus P by rho. Okay, so this is the term that we are going to put into this equation. Okay, so we are going to just replace the internal energy and we are going to replace it with the enthalpy energy. Okay, so let me first write these two terms, because these are the only two terms that are involves the internal energy. So if we write del rho del E upon del tau plus del dot rho u e. Okay, now we can replace this equal to H minus rho P, so we will have rho del H upon del T, okay, minus this rho will be cancel out and we will have del P upon del T. Okay, now plus there will be these terms, so del dot, so if we replace equal to H minus P upon rho, then this a term will be left like del rho u H minus this rho will be cancelled out and in place of will be P, so we will have del dot up. Okay, so this is these two terms can be replaced into these four terms, we are going to just put these four terms in these equations, and we can have this rho h upon del t minus del p upon del t plus rho uh minus del dot up. Okay, so these two terms will be replaced with these four terms, and plus rho del k upon del t, that is the capital K. Okay, plus del dot rho u capital K equal to minus del dot q. Okay, plus tau del dot tau into u minus del dot up. Okay, and plus this is the potential term, that is the rho g into u. So here you can cancel out this minus del dot up into del dot up, and the rest term will be the final enthalpy term. Okay, so let me just rearrange this. Capital K upon capital T, capital K upon small t. Okay, so there will be minus del P upon del T. Okay, that is generally different from the internal energy. So these terms you are not going to find in the internal energy equations, plus rho g into u. Okay, so this is the energy equation that can be written in the form of the enthalpy. Okay, and that is the energy equation that we have written in form of the internal energy. Okay, so when you see the energy equation in OpenFOAM, these are the two energy equations that we are going to solve. So if we switch for the internal energy, so this equation is going to be solved, and if we switch for the enthalpy energy, then this is the equation that is going to be solved. Okay, now when we are going to solve the energy equation, generally you are going to see that this contribution and this contribution is being ignored in the most of the solvers. Okay, so if there is no specific requirements, then this terms is being ignored, because the contribution due to the strain energy and the contribution due to the change of the potential energy is negligible. That is why these terms are being ignored the most of the solvers. However, when there is some specific requirements, for example, if you are going to see the solvers like rho central pimple form, then you are going to see these terms. Okay, so similar cases, when there is a specific requirements, then you are going to see these terms. Okay, so these are the two equations that you are going to solve, and this is the equation that is the heat flux. So speaking of the heat flux, that is written as the del into Q, that you can find in the OpenFOAM written in the terms of the effective diffusivity term. Okay, into the either E or H. Okay, so if you are going to solve in terms of the enthalpy, so it will be the H. If you are going to solve in terms of the internal energy, then it will be E. Okay, now what is the alpha effective? So this will be contribution from the turbulent, or there will be contribution of the laminar. Okay, so there will be laminar thermal diffusivity, and there will be turbulent diffusivity. Okay, and how these terms are coded in the OpenFOAM. So how you are going to get the effective diffusivity due to the turbulent and effective diffusivity due to the laminar, that we are going to see while we are going to show the actual codings in the OpenFOAM. Okay, so I think this video is already too much longer, so the coding perspective here I am going to explain in the next tutorial. These are the resources that I have taken to create this video. So if you want to further study about this context, you can go through these references. So thanks to all of you for watching this video, and please stay tuned to my YouTube channel.